Okay, so today we're going to learn a rule of integration, kind of like, how we have the product rule, quotient rule, that allowed us to find derivatives of functions by following a specific rule. The substitution rule is a method we use to find antiderivatives of functions that don't look that simple to find antiderivative of just by looking at it. So this actually simplifies things for us. So let's just start off with an example. So if I said, for example, find the integral, the indefinite integral of x plus 2 dx, you should all be able to do this, right? Just by looking at this, we could see right away that this we could find the antiderivative of, and we could use the shortcuts because this is x plus 2 to the power of 1/2. So this becomes 2/3 x plus 2 to the 3/2 plus c. So when you take a look at this, you say, okay, look, I could find the antiderivative of this, and that's not difficult because we did this. Now, the x plus 2, remember, because of the chain rule, the derivative of the inside is just 1, so it doesn't really affect this. So when I find a derivative of this, I get back to that. So now my question would be, now find the integral of 2x, x squared plus 2 dx. And so if you want, this should be a 2x. And if you want, find, here, let me write it up here again so it's clear. It's 2x square root of x squared plus 2. So if you want, you should try to maybe pause the video and try to find this by hand, okay, and take a few minutes and see if you could find it. And if you've already done so, you're probably kind of like stuck here because as you're trying to find shortcuts to use, you see we have a problem. However, what we notice is this becomes more difficult to find using our current integration methods. Okay, in fact, it kind of becomes almost impossible, right? When you look at this, you're like, oh, I don't know, I'm kind of stuck. How would I find the antiderivative of this? So here's where the substitution rule comes in, and it's just going to simplify this so much for us. So here's what the substitution rule says. Or I'll kind of walk you through the substitution rule first, and then I'll give you the official substitution rule, because I think once we go through the kind of the notions, the motions of what we need to do to get this, then you'll get a better idea. So it's usually known as U sub. So whenever we say use U sub, we're saying use the substitution rule. Okay, so the first comment I want to make is the following. We could say, look, notice how there is a relationship with x squared plus 2 and 2x. Okay? And my question to you is, if you look at this, you would notice that the relationship between x squared plus 2 and 2x is that they are derivatives or anti-derivatives of each other, right? If you look at this, the derivative of x squared plus 2 is 2x. The antiderivative of 2x is x squared plus c, but in this case, c is 2. So they have that relationship. So when you could spot a relationship like this, probably U sub is appropriate to use. So if you see an integral that looks complicated, and you say, but wait a minute, if I have to find a derivative of this and I get that, then U sub is probably the way to go, okay? And of course, sometimes the U sub isn't as obvious as like this case. So we'll do some examples and you'll see this. So we could say, so since this relationship exists, we're going to let u equal to the x squared plus 2. So notice how what I'm letting u equal to is the antiderivative of the 2. So since x squared plus 2 is the antiderivative of 2x, I'm going to let u equal to that. Okay? So then what we should notice is this. Let's kind of start updating our integral. So this integral now, since u is x squared plus 2, here's what we get. We get now the integral becomes the integral of 2x u dx. And notice, what is it that I don't like? When you look at this, it looks worse than that, actually, because what happens, now I have x's and u's, and see, this integral is saying, this dx is saying, look, everything has to be in terms of x. So although u is kind of, you'd say, oh, is this a constant? In fact, it's not, because u is a function with respect to x. So what I want to say here is that we still don't like this. Right? If anything, it kind of looks like it became worse. So our goal is now, so we're going to say, in fact, our goal now is to write 2x dx, which is basically what's left in terms of x, in terms of u and du. So somehow I want this dx to become a du and that 2x, or the 2 we don't care about, it's a constant, but the x to become a u. So here's what we could say. We can now say, look, since u equals to x squared plus 2, then using first semester things, ideas, the derivative of u with respect to x, which in Leibniz notation looks like this, du dx equals to dx. Now look at what I'm getting. Du dx equals to 2x, which what does this imply? If I multiply both sides by dx, this means du equals to 2x dx. And I'm going to put just a bunch of exclamation points after that, because look at how nice this is. Our 2x dx that we want to write in terms of u and du actually just ends up being du. So our new integral now, now becomes integral of square root of u du, because the 2x dx becomes just a du. Now look at how nice that is. I mean, this is such an easy integral to find. Okay, now coming back here, one comment I want to make. When you find the derivative with respect to x, you get this, and you multiply both sides by dx, you're going to get so used to this where you don't have to say du dx is 2x. You could just say du is 2x dx. It's kind of like you're doing two steps in one, because from here to here, what did I do? I multiply both sides by dx, which gave me that expression. Okay, but remember, we're first finding the derivative with respect to x, and then we're multiplying both sides by dx. But commonly, what people do is when they find a derivative of this, which would be x 2x, they just multiply dx from both sides to both sides. So they just write du equals to 2x dx without this kind of step in the middle. Okay, but it doesn't matter. So if you want to go through all the steps. So going back to this, what does then this become? This then becomes 2/3 u to the 3/2 plus c. Okay, now u substitution is just a method that allows us to integrate this guy right here, this guy. Okay, so what that means is my final answer shouldn't be in terms of u, it should be in terms of x. So now that I used substitution to help me integrate, now I could substitute back. So we'd say, look, substitute back in for u, which then results in 2/3 x squared plus 2 to the 3/2 plus c. And there you have it. So we were just able to find the antiderivative of this using the substitution rule. Okay, so as you can see, the substitution rule is a very important tool to have to find antiderivatives of functions that look fairly complicated, but the substitution rule simplifies it. Okay, so let me give you the substitution rule, and then we'll do a couple of examples, and then we'll also use the substitution rule for definite integrals, which the thing doesn't change, the process doesn't change, except we're going to get a numerical answer. So here's what the substitution rule says. If u equals to g of x. So let u, kind of like what we did there, right? You assign u into some function. This is a differentiable function whose range is an interval I and f is continuous on that interval. Okay, so we'll see why in a minute that f has to be continuous on the range of g of x. Um, then here's what we have: the integral f of g of x, g prime of x dx. So look at what's happening here. See, why do I want f to be continuous on g's interval? Because the outputs of g has to make sure that f is defined. If f is undefined, it won't work. So notice what's happening here. There's g and g prime, which, what do you notice here? There's a relationship between derivatives and antiderivatives. See, if I find a derivative of g, I get this guy. If I find an antiderivative of g prime, I get that guy. So that's kind of what we're seeing here, which if you see this, then what you could say is, look, if I see this property, then g, I'm going to let it equal to u, and then the derivative of u will become g prime, which then the g prime dx will become just du, right? Because if you look at this, the derivative of u with respect to x would be what? Du dx equals to g prime of x, and if I multiply both sides by dx, I get g prime of du equals to g prime of x dx, which that's what happens here. So this is going to be the integral of f of u du. And see, this function, if we go back to this original function, our function was the square root function, and everything else became in terms of u. So that's what this is saying. So then if you integrate this, then you have the antiderivative of this, and then you could plug back in for u. So this, basically what this is saying is we did up here. Hopefully this probably made more sense to you, because if I gave you this with the symbols first, you might have been like, well, hold on, what's going on? But now you could easily follow what's going on here, right? Because we let u equal to g of x, then du equals to g prime of x dx, which, so then this becomes du, that becomes u, and that's what you get this, and then you could easily simplify that. Okay, so let's look at a couple of examples, and maybe you'd want to kind of try to do these examples on your own first, and then come back and you know, look at it or compare it to what I do. So if I say find the integral of x cubed times cosine of x to the fourth plus 2 dx, so if you look at this, right away you see a pattern. See, you notice that, look, the derivative of x to the fourth plus 2 gives me x something in terms of x cubed. So u substitution is the way to go. So we're going to say let u equal to the x to the fourth plus 2. And what does that mean? Du will be 4x cubed dx. And see, what's the problem here? I don't need 4x cubed dx, I need x cubed dx. So remember, constants I'm not concerned about, because how could I fix this? Just divide both sides by 4. So what does this mean? 1/4 du equals to x cubed dx. Okay, so what does this turn into? This integral now becomes x cubed dx is going to be 1/4 du, and then so I get 1/4 cosine of x to the fourth plus 2 du, right? So this 1/4 du came from x cubed dx, and then, oops, that should be just a u. And the x to the fourth plus 2 should just become a cosine of u. Okay, so once I have that, let's also move this 1/4 out front, because we have a property of integrals we could use there. So what does this become? Cosine of u du. And look at how nice that is. This just becomes so much easier. I'd much rather find the antiderivative of this than that. Okay, because this does the job. I just need to substitute back. So what does that become? The antiderivative of cosine is just sine. So it'll be 1/4 sine of u plus c, and then you plug back in for u. And you could also distribute the 1/4. So it'll be what? 1/4 sine of, and u was x to the fourth plus 2 plus c. And look, 1/4 times a constant is a constant, so I'm just leaving that as plus c. So it's not that I forgot to multiply this constant by 1/4, but we're just saying, look, what 1/4 times this constant, whatever that constant may be, just call it plus c. You know, if they want us to find the constant, then some extra information will be given, but for now, that's what it is. Okay, so moving on to example 3. So this one will be find the integral of square root of 1 plus x squared times x to the 5th dx. Okay, now for this one, see, this becomes a little more complicated. See, we're going to use the u substitution, but it's not as obvious as before. Now, obviously, if we were to look at this, what's the problem? If, let's say, I were to let u equal to x to the 5th, when I find the derivative of this, I would have to get a square root of 1 plus x squared, which that becomes complicated. So whenever you see something like this, you're probably better off letting u equal to what's inside of the square root, because x to the 5th would be easier to force out as opposed to the derivative of x to the 5th has to somehow become a square root, and it has to have a 1 plus x squared in it. So we could see that that becomes more complicated. So for this one, we're just going to say let u equal to 1 plus x squared. So then what does this mean? Then du equals to 2x dx. Okay, so when we get that, here's the problem. First of all, this doesn't even have a 2, so what does this imply? We could say 1/2 du is equal to x dx. Now, obviously, this has an x dx in it. See, if I were to kind of take this down here and say this integral will now become what? Square root of u times x to the 4th x dx, right? Because why do I take away an x from this? Because what do I know? This x dx is going to have a 1/2 du. Now the problem is we also have an x to the 4th. How do I fix for that? And so the good news is x to the 4th I could force out of it, because if I come back up here, notice how I have an x squared here. So how could I get an x to the 4th out of this? Just square this guy. So we could just simplify and write this in terms of u. So subtract 1 from both sides, and you get u minus 1 equals to x squared. And then if I square both sides, I get x to the 4th equals to u minus 1 squared. So now I could go ahead and complete this. And look, there's something going on that I like about this, okay? What's the problem here? See, this I can't distribute right now because the square root has a binomial in there. But once I make, now notice here, the square root here has a monomial in here, which just going off to the side, if I were to say, just off to the side, let me just make a comment like this. If I gave you something like this, can't you distribute those? Because you could say, yeah, you know, square root of x is the same thing as x to the 1/2, and I could just distribute this, and then that would make it easier to work with. However, if I have a binomial inside the square root, it becomes harder to distribute. In fact, I can't distribute it as easily. So using u substitution here, it's not that it makes it look any easier, but it allows us to simplify. So look at what happens to this. This becomes the integral of the square root of u times x to the 4th is u minus 1 quantity squared, and then that'll be what? 1/2, x dx is 1/2 du. So I'll put the 1/2 out front, du. So from this point on, we could just start simplifying. See, this square root of u, I'm going to treat it as u to the 1/2. So this will be 1/2 square root of, or integral of u to the 1/2, and then u minus 1 squared is what? U squared minus 2u plus 1 du. Now look at what's nice about this. I could distribute this. So if I distribute the u to the 1/2, I get 1/2 integral of u to the 1/2 times u squared is u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. Now look at how nice this is. I could find the antiderivative of this, right? Because all of these give us nice results. So this becomes 1/2 times, what's the antiderivative of u to the 5/2? That's going to be 2/7 u to the 7/2 minus u to the 3/2 will be what? U to the 5/2, and this would be 4/5. And then plus the antiderivative of u to the 1/2 would be 2/3 u to the 3/2 plus a constant. Okay, and so once you do that, you could plug back in for u, distribute the 1/2, and then that should be good. So I'm going to do both in one. So if I distribute the 1/2, what does that become? 1/7. And what was u? It was 1 plus x squared. 1 plus x squared to the 7/2 minus 2/5. 1 plus x squared to the 5/2 plus 1/3. Or sorry, yeah, it should be 1/3. 1 plus x squared to the 3/2 plus c. Okay, and so there you have it. So notice how nice this was. So use substitution just makes things more convenient for us. And for the last example we did, it wasn't as obvious, but usually whenever you see a square root of something with a bunch of things in it, like it's not a monomial, times some monomial, then you should consider using square root. And in fact, you want to switch the roles. You want this guy, you don't care if this guy has a monomial inside the power, but you want this guy to have a monomial inside the square root. How come? Because then we could distribute it. It just makes it so much easier to work with. Okay, so kind of this one, like I said, it was u sub in disguise. It wasn't as obvious, and we had to manipulate it a little more just so I could write everything in terms of u. But once you do that, then just to simplify out, it becomes such an easy integral to find the antiderivative of. Okay, so moving on. Let's look at one more example, and then we'll talk about the substitution rule for the definite integral. So if I were to say find the integral of tangent of x dx. So when you're doing this, what you notice is, wait a minute, I could probably write the tangent of x in terms of sine and cosine, which would be sine x over cosine x dx. So here's the deal. You could let u equal to sine or cosine. It looks like both would work, but here's the problem. If I let u equal to sine, then what do I want? I want the derivative of sine not to give me cosine, but I want it to give me 1 over cosine, because think of it this way. If I were to rewrite this as sine of x times 1 over cosine of x dx, I think this makes it more obvious. See, if I let u equal to sine, then the derivative has to be 1 over cosine, which that's a problem because I can't get 1 over cosine. I know that the derivative of sine is cosine. So if I were to let u equal to cosine, then all I would need is sine x dx, which the derivative of cosine has sine in it, which that's the good news. So the reason why I want to stay away from assigning u to sine is because I can't get 1 over cosine out of it. So what we're going to say is let u equal to cosine of x, then du will be negative sine x dx, which means negative du is sine x dx. And then the rest becomes straightforward because sine x dx becomes negative du. So this integral now becomes negative integral of 1 over cosine is u du. And look at how nice that is. The antiderivative of this is ln of absolute value of u plus c. And then now you could plug back in for u cosine. So that'll be absolute value of cosine of x plus c. So what did we just do? We just found out that the antiderivative of tangent is negative ln absolute value of cosine of x plus c. Okay? Or if you want, you could simplify this some more. You could take the negative to the top. Some books may say it's ln of secant of x plus c. Now, why they do that? They took this negative 1 to the top and said cosine to the power of negative 1 is 1 over cosine, which is secant. Okay, so they're the same thing. Okay, so whichever one of the two you write, they should give you the same thing. Okay, but I think more books have that. They just kind of said, let me move the negative up there. Okay, so now let's talk about the substitution rule. For definite integrals, which for definite integrals, remember, we expect to get numerical solutions. So here's what the substitution rule says for definite integrals. So if g prime is continuous on the interval from a to b, and f is continuous on the range of u, which we have set to g of x, then the integral from a to b of f of g of x times g prime of x dx. So we're still going to use substitution, the u sub. G is going to turn into u. G prime x dx was going to become du, but this becomes g of a to g of b f of u du. So the process is the same, but one comment I want to make here that's different is, of course, notice how the lower and upper limits are changing. So the comment I want to make is that all this says is that we need to fix our lower and upper limits with respect to u. So look, the reason why what's going on here is this. Right now my variable here is in terms of x, okay, which means a and b are x values. Now when I change my variables here in terms of u, the a and b also need to change. So these have to be u values. So these x values, I need to translate them in terms of u. So that's not that difficult to do. In fact, this changing a to g of a and b to g of b, those are not difficult because those are already predetermined. We can change those to u's, okay? Because after all, look, u is what? G of x. So if x is a, what's u? Well, plug in a into x, and then you'll get your u value, and that's what g of a will be the u value, and g of b will be the u value corresponding to that x value, and so on. So that's not difficult to do because these guys you've already predetermined. You've already, through substitution, you could find these easily. So let's look at our last example, and then we'll talk about integrals of symmetric functions, and that'll basically do it. So I believe this is example 5. I would say evaluate the integral from 0 to 4 of the square root of 2x plus 1 dx. And so what I notice is I want to use u sub again, and the only thing I could let u equal to is what? 2x plus 1. And then when I find a derivative of this, I just want dx out of this. So we're going to say let u equal to 2x plus 1. And what does that mean? du would be 2 dx, except I just want dx. So what does this mean? I get 1/2 du equals to dx. So, and here's the other nice thing. For an indefinite integral, if you remember, we had to go back and substitute back in for u to get everything in terms of x. For a definite integral, since my answer is going to be numerical, at the end I'm not going to have any variables. So I can just leave things in terms of u, and I don't ever need to substitute back. For an indefinite integral, if you're integrating with respect to x, your answer has to be in terms of x at the end. But in this case, since this is a definite integral and we want a numerical solution, you don't ever need to go back and substitute back in for u. That's kind of like a nice result we get for this. So what does this become? This is the integral. Now, it shouldn't be from 0 to 4 because, look, I'm changing everything in terms of u. So look, when x is 0, how could I find out what u is? Well, doesn't this give you the relationship between u and x? U equals to what? 2x plus 1. So if you tell me what x is, I could tell you what u is. So if I grab 0, plug it in here, I get 2 times 0 plus 1, which this ends up being 1. So when x is 0, u is 1. You guys see what I did here? I hope you did, because all I did is I said if u is 2x plus 1, so if x is 0, u equals to 2 times 0 plus 1, which that's how I got the 1. And then how would I get that? How would I translate this to in terms of u? Well, when x is 4, plug it in here, you get u is 9. So when I switch from x's to u's, I also have to change my lower and upper limits in terms of u's. So once we do that, then the rest becomes straightforward. The rest is what we did earlier. So this becomes what? Square root of u and 1/2 du. So I'll put the 1/2 out front, du. And there you have it. So now I could find the antiderivative. So this is 1/2 times the antiderivative of square root of u is what? U to the 3/2 times 2/3. And remember, since this is a definite integral, I don't have to put the plus c. and it's from 1 to 9. So now notice how I'm ready to plug in 9 and 1. I don't need to go back in terms of x. So this becomes 1/2 times 2/3 times 9 to the 3/2 minus 2/3 times 9 or times 1 to the 3/2, which that becomes 1/2 times square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is 9 times 2, which that's 18, minus 1 to the 3/2 is 1, which will be just be 2/3. Okay, and then when we have that, this is what? This becomes, I could first distribute the 1/2 just to make these numbers smaller. It doesn't matter how you simplify, which this becomes what? 9 minus 1/3. And 9 minus 1/3 becomes 26/3. Okay, so how you simplify is up to you, but let me show you this, and that's basically it. Okay, so the last thing I want to talk about to wrap up this section is integrals of symmetric functions. So these are simple. At least one of them is extremely simple. It doesn't require much math, which you should probably pay attention to symmetry when you're finding antiderivatives, because sometimes if you don't pay attention to symmetry, then your life will become super difficult because you'll be doing a bunch of calculations where you don't really need to do it. So let's write this out. So we're going to say, so this is integrals of symmetric functions. So I'm going to say, suppose f is continuous from -a to a. And what's key is these are exact opposites. So these symmetric functions, obviously, we have to start from opposite values. So whatever this is, this has to be the exact opposite. So remember, this only applies when I'm going from -a to a. So look at this first comment we're going to make. We're going to say, look, if f is even, which we know what it means for it to be even, f of -x equals to f of x. It's symmetric with respect to the y-axis. Okay, then the integral from -a to a of f of x dx equals to, and see, we could probably make sense of this. See, if you think about it, let me draw this out. See, if f is even, what does that mean? It should be symmetric with respect to the y-axis. So if this is -a and this is a, if I find the area under the curve from -a to a, which is this, and what do you notice? Hopefully you're noticing that, look, this area and this area, they're both the same. So how could I adjust this to make my life slightly easier, right? This makes it things a little better for us. What could we say? We could say, look, find the integral from 0 to a of f of x, or find the area under the curve from 0 to a of this guy, and then what should you do? Since it's symmetric with respect to the y-axis, just double it, right? So basically what we're saying is, if I take this area and double it, it'll be the same thing as taking the integral from -a to a. So that's what this allows me to do. It kind of makes it easier. Why? Because then I'm starting from 0 and I'm going to a of this function, and you double it. But remember, my lower and upper limits have to be exact opposites. If they're not, see, if let's say this is my lower limit and that's my upper limit, clearly the area on the left is smaller than the area on the right. So this has to be with the lower and upper limits have to be exact opposites. Okay. Now part B, which is even more convenient and makes things even much more simpler. If f is odd, which what does that mean? F of -x equals to -f of x. My y values are exact opposites at opposite x values. Then the integral from -a to a of f of x dx. See, we could do much better than part A in this one, because look, if I give you a function that's odd, maybe it should do something like this and like that. And if this is -a and this is a, what do you notice about this area? Let's call this a1 and a2. What do you notice about this area? This area is positive, this area is negative, and they're the exact same areas because it's an odd function. So these areas basically counteract each other. So what we notice is, since the areas are opposites, what could we say? This implies area 1 plus area 2 should equal to 0. So what do you notice? This integral will be 0, which that's really nice because anytime you have an odd function and I'm asking you to find the area under the curve of this odd function and my lower and upper limits are exactly opposites, there's nothing to think about because what we know is that these areas are going to cancel each other out, so you're going to get an integral of 0. Okay, so just keep your eye out on this, especially when you see limits that are exact opposites. Check for symmetry because it might make things easier for you. Okay, so that wraps up this section. Um, and we just have basically one more section left of this chapter, and that'll basically do it. Okay, so I hope you like this U substitution because it just makes things so much easier for us.